Okay, so this is our approximate rate function, which we've been working hard on from the sliding interval, right? The sliding interval of width h, and we get that secant line that cuts through the curve, gives us 2 points, and we're going to find the rate associated with that secant line as an approximation to the rate at the beginning of the interval, right? So we take that, got some curve like this, and we've got our current value of x, which could be any x, and then we've got some. So what's this x coordinate right here? X plus h. This is our amount or accumulation function f. And we know if we want the rate of change from x to x plus h, the rate of change that achieves the same change in y, we're going to take change in y over change in x. So change in y, f of x plus h, y value there, minus f of x, y value there, over h, the change in x. That'll give us an approximate rate, what? That's approximating the rate at this x value, at the starting x value, right? So it's approximating the rate right there. This is called the difference quotient. Why? Because it's one difference divided by another difference. Change in y over change in x. We call it the difference quotient. And it approximates the rate of change of some function f. And then as x changes, it gives us a function for rate of change, right? So as x changes, we get approximates for all the rates of change for all the values of x. Okay, so we looked at this particular amount function, the amount of volume of a sphere, or the accumulated amount of volume of a sphere. And we said, what does that rule tell us to do? It tells us to take the independent value and do what? Cube it, and then multiply it by 4/3 pi. Right? So a rule of a function is just a set of instructions on what to do with the value of the independent variable. This set of instructions is cube that value, take 4/3 pi of it. Okay? So we're going to do that. What's our independent value here? X plus h. So we're going to cube it and multiply it by 4/3 pi. So we're going to cube that independent value, multiply by 4/3 pi, and then similarly, when x is the independent value, we're going to cube it and multiply by 4/3 pi. And then we need what? The change in y. So it's going to be that first minus the second. So what's the most common mistake students make with this f of x plus h? They say, oh, it's 4/3 pi x cubed plus h. That's the most common mistake. But it's not. X plus h is your independent value. So it has to follow the set of instructions that the function gives. You know, it's not just adding h. You're not just adding h to the rule. That's the most common mistake. All right, and then we're going to take that divided by h. Okay, and so then I gave you, and then we say that this is our approximate rate function. It's just r. Okay, and so this is actually now a closed form, right? Because we could give it values of x and h and it would spit it out, but we want to simplify it, a much more simplified version of this. So we could do some algebra. So let's go to GC and see that. This is what we're going to do on Friday. Didn't have time. So let's see how GC can help us with this. This one. Okay, so there's our sphere problem. Down here. GC can do cool stuff, but if you know what you're doing. All right, so here we go. There it is. So we can type that into GC like that. That's what we just came up with, right? So I'm going to copy that, start a new line, paste. Okay, so what do we want to do? We need to simplify that numerator. Simplify that numerator. So what do we need to do first? We need to expand out x plus h cubed, right? X plus h cubed There's some algebra to do there, so we can do that algebra. We can go to math, and we can do expand. Right? So GC can do the algebra for us. But this is not nearly as cool as seeing exact functions become approximate functions by making h small, right? That's much cooler. But this is okay. This is okay. All right? Okay, so what's next? So notice we've got 4/3 pi. Actually, so we can, let's see, we've got 4/3 pi in both of these terms here. So I can, if I grab it and pull it out, it factors it out. You see that? So that's what I had before. So let's copy and paste that. So copy, paste. All right. So now you can, since 4/3 pi is in both, I can grab that and pull it out. Oh, what happened? Something happened when I went around the bend. So I need to get rid of these. There we go. Yeah, so I got to start over. When I returned it back to its original form, then it didn't like it. Okay, so here we go. So I got this. I'm going to grab on the 4/3 pi, pull it out. Oh, expand, right? I can expand now. Okay, so now I'll expand. There we go. Okay, so now look what do you see inside now? We've got the very first term is plus x cubed. The last term is minus x cubed. So those go away, right? X cubed minus x cubed is 0. So I can highlight on that, and I can simplify. Okay, so it just took the x cubed minus the x cubed. All right, and then what now? Notice what I have in all of these terms now. H, right? So I can grab an h and pull that out. And this is the step we need here, because that h in the denominator is what causes problems, right? And so now we've got h over h. I factored out h, I got h over h. No, so you're looking at this. It did. I just repeated it, right? So it pulled one h out of there, one out of there, one out of there to get that, and then I copied it. All right, so now h over h is, and we can simplify again. And so this is about what we had last time, except the 4/3 pi was distributed back in. Okay, so expand out that x plus h cubed, factor out the h, and when you factor out the h, then h over h becomes 1, and so now we no longer have an h in the denominator. So this is where this now, we can talk about h getting really, really small, right? We can see what happens when h gets really, really small. It's hard to see algebraically what happens when h gets really, really small if we've got h's in the top and the bottom, right? So who knows, right? So when h gets really small in that first expression, it's hard to tell what's going to happen. But when we can do the algebra and get that h out of the denominator, now it's easy to see what's going to happen when h gets small. So let's go back to that PowerPoint. So this is what we ended up with if you multiply that 4/3 pi back in. Okay, and so then we said, so now we want h to get really small, because this is still approximate rate, right? Approximate rate. So when h gets really, really, really small, this thing becomes what? 4 pi x squared when h is essentially 0. And we use this symbol to mean that. So this is the same principle we talked about before with integral. Small enough that you can't tell the difference between exact and approximate. Right? Small enough that you can't tell the difference between exact and approximate. That's what this h essentially 0. But it can't be 0 because we have to have a moment, right? We have to have a little change, at least a little one, right? So you say essentially 0. And so then we get, this is our exact rate function in closed form for the volume of a sphere. Okay, so I could do something like r sub f of 7. And if I do r sub f of 7, what would that be? 4 pi times 49, or is that 196 pi? Okay, so I want you to have a conversation, and I want you to interpret r sub f of 7 equals 196 pi. I want you to give as much detail as you can. What does r sub f of 7 equals 196 pi mean? Okay? And don't just say, it's the rate of change. That's not sufficient. Yes, it's the rate of change. It's the rate of change. What rate of change is it? And then what does that rate of change mean? Talk. Go. Given, so what do we say? Given what? Who remembers the meaning of rate of change? It's still important. Kyle. What's that? Okay, so tell me what's MDX in this situation? Okay. So given a small change in radius, given a small change in radius around 7, someone continue, someone new? Given a small change in radius next close to 7. Yeah. And what's y? What's y? Right. The corresponding change in volume for that change in radius will be 196 pi times that change in radius. Okay, so based on that, can you, using that fact to estimate f of 7.03? F of 7.03. Someone in the back think they have it? No? Kyle? Yeah? No, we're doing an expression. Don't do any calculations. Okay? Right? Which would be? That's right. So, yep, so we can get the change in y. What's the change in x? The change in x is from 7 to 0.03. The change in x is 0.03. Do you see that? We see that that change in x is 0.03, so the corresponding change in y for that change in radius will be 196 pi times 0.03. And that's our change in y, so then, or a change in volume. So then we're going to add that to the volume that we would have at 7, which is f of 7. And that would give us, that would approximate the volume at 7.03 for radius. Okay, anybody have a question? So that was just kind of a little review question from the past. But the point here is that we've got this very convenient closed form rate, or closed form representation of the rate function. I told you that the radius was 7, and boom, 196 pi. That's the rate of change at 7. And then here's how we could use that, okay? So let's try another example. Okay, so if f is the area of a square, we've seen this, fx equals x squared. We want to find f's rate of change function. We want to find it represented in closed form. We want to find f's rate of change function. We want to find it in closed form. So we're going to start with what we know is the approximate rate of change function. So what is, somebody new, what is the approximate rate of change function for a function f? This is where we live in the next couple weeks. What's the approximate rate of change function for function f? How about in the Let's Go Devil shirt right here? Not sure? Okay, yeah. Okay, before that, just for any function f. So for any function f, yeah, you're right, but for any function f, what would it be? Okay, so this is always the rate of change function for any function named f. Any function named f, this is the rate of change function. It's just approximate, right? If h is large or not small, then it's approximate. And you said that was, so for people who didn't get that yet now, so no, we've got the function x squared. So your next step is to apply the rule of the function x squared and rewrite that difference quotient. Everyone do it. Rewrite that difference quotient. So let's see. White t-shirt right here. What is f of x plus h for us now? F of x, what is it? X plus h squared, right? So f of x plus h, so this is a really easy rule, right? It says take the independent value and square it. So what's our independent value? X plus h. So the function tells us take that and square it. F of x is over. Okay, so now this would be faster to do by hand than with GC, right? So because we know this is pretty basic. So x plus h squared is. Do I have this all programmed in here? X plus h, so it's x squared plus h squared, right? You should be thinking no. Although many, many calculus students have tried x squared plus h squared in the past. There's a middle term, right? There's a middle term, 2xh, okay, minus x squared all over h. What happens now? So our goal to make this simple, right? So this is it's not simplified, and also it's got this h in the denominator. So we want to simplify this, try to get that h out of the denominator. That's our goal. So we get x squared minus x squared. It's gone. It's 0. So 2xh plus h squared over h. And now we've got all h's. Every term has an h. So we can factor it out. So we get so we get 2x plus h. H over h is 1. So it goes away. Okay, so is this approximate? Is it exact? Is it rate of change? Is it accumulation? Is it open form or is it closed form? So tell the person next to you. Is it rate of change or accumulation? Is it approximate or exact? And is it open form or closed form representation? shirt. You looking like, no, green. Green sleeves. Yeah, that's you. Green sleeves. What do you think? So is it accumulation or rate? Rate of change, right? It's still equal to R of X, right? It's still equal to R of X. All these things are a string of equalities, so it's still R of X. It's rate of change. Okay? Approximate or exact? Exact rate of change. Agree with that? No, because if H is not small, this is still approximate. It's still equal to this. So it's rate of change, it's approximate. And then is this an open or a closed form expression? Closed. It's easy to crank out, right? Easy to crank out. Values of 2x plus h, given an x, given an h, boom, just rapid fire, you get them. Okay, so how do we get exact? Yeah, we just let that interval get essentially 0 or really, really small, and we get 2x. So we get that our exact rate of change function is 2x. And so what is this? This is the function that tells us the rate of change of the area of a square with respect to the side length, right? So we could do something like, we could interpret this and estimate. We'll do this on your own time. So here's a good little exercise. We'll make that for Wednesday's homework. Interpret this. Fully interpret the value of 20. Write an expression that estimates f of 9.98 and interpret. Okay, so that'll be a good little exercise. All right, so let's talk about then, having found this rate of change function 2x from the function x squared, let's talk about what we've achieved for ourselves here. What did we do? We just learned that if f of x equals x squared, the rate of change of f is 2x. So if we have a rate of change function, given a rate of change function, how can we express the accumulation? How can we express accumulation given a rate of change function? Aiden. Right. That's so given a rate of change, how do we express exact accumulation? Nice and loud. Integral, right? Integral. So can you write express f if its rate of change is 2x. Express f if its rate of change is 2x. Everyone write it down. If you can. You should be able to. Right here. She's writing. Yeah. Did you get it? Okay. Did you get it? Tell me. Almost. The integral from a to x, 2x dx. Just one small change. You need a new variable for the inside, right? New variable for the inside. Yeah. So, and since we start accumulating, so we can do 0. Since we can think of the area of the square accumulating from 0. So this is what we learned before. If you have the rate function 2t, that can be expressed as the integral from 0 to x 2t dt. Okay, so this is the key. So by finding that the rate of change was 2x of x squared, we not only found that rate of change, but we also found out that when the rate of change is 2x, what is the closed form of that accumulation function, right? So before we only could express this, and we couldn't go any further, but now we have the closed form of f, which is what? right? It's x squared. So every time we find a rate of change function in closed form, we make note of it so that when we have that as an integral, we know what the closed form accumulation function for that integral is x squared, right? So we could write the integral from a to x 2t dt as x squared for some value of a. In this case, that value of a is 0, okay? All right, so you try this, okay? So earlier we learned that the rate of change function for the volume of a sphere is 4 pi x squared. So what else did we learn? So given that the volume is 4/3 pi x squared, by getting the closed form representation of its rate of 4 pi x squared, what else did we learn? Can you write out a statement that shows what else we learned as a result of that? Super important. Everyone write it out. What else did we learn from the fact that 4 pi x squared is the rate of change of 4/3 pi x cubed? Yeah. Okay, of what? Nice and loud. So integral from a to x equals what? So she said the integral from, if we had this open form accumulation function for this rate of change, right? Sorry. We now have that, a closed form for that. What is the closed form for that? What's that? 4 pi x squared? No, if that's the rate, then our closed form accumulation is, Jacob. Right. Oh, I guess that's not in the PowerPoint. So that's all right. Okay, so yeah. So if we have this accumulation function expressed in open form where the rate is 4 pi, geez, I did it again. What we know that is for some value of a. Again, in this case also when a is 0, for some value of a. So when we're in the next couple weeks, we're going to be finding lots and lots of closed form rate of change functions from accumulation functions. Every time we do that, we want to make note of, look, every time we solve and get a closed form rate of change function, we just enabled ourselves to get a closed form accumulation function that before we could only express as an integral. Huge point. So that's why we want to generate lots and lots of these rate functions, because it allows us to generate lots and lots of accumulation functions in closed form. By taking it, it's basically the function we started with when we found its rate. Okay? Because there is nothing we can do algebraically to get this. We have to do the reverse process to get closed form rate function, and then that tells us what the closed form accumulation function is, the one that we started with. Okay, really important point. So keep reading in the text, mulling over that. There'll be a few additions to the homework due Wednesday.